So this lesson is on line integrals for work. And let's remember that work is a force times a distance. So recalling our work done earlier in calculus, what would our total work be? Well, it is a sum of the force times the change in distance. That's what you want to keep in mind. So we're working on a line integral. We imagine we have a curve C, and we consider that curve being in a vector field. So at each point on C, there would be a vector, a force for us to consider. So if we're here, maybe this is our force F. Now, we want to consider how that force is acting in the direction that C is heading. So we're interested in the projection of that force onto the tangent vector T. So if I consider the unit tangent vector T, let's go ahead and draw that in. So this is the unit tangent vector T. The portion of the force in the direction of the unit tangent vector is what we're going to want, because we're going to break this up into a very, very small change in distance. Let's call this change in S. A very, very small change in S. How much force do I have going in that distance? That's the work that's done from here to here. So what I need to get is I need to consider the projection of F onto T and then look at its magnitude. So recalling from earlier, the projection of F onto T is F dot T over T dot T times T. Then how about the magnitude of the projection of F onto T? Well, that would be what? That would be F dot T. I'm gonna ignore the absolute values because it's either going in the forward direction or the backwards direction. So I want to keep it just as F dot T. T dot T is the magnitude of T squared, right? And then T, magnitude of that is just magnitude of T. But again, to be perfectly legitimate, I'd have to go ahead and call this absolute value of T or the magnitude of the projection, but I want to keep the plus or the minus, so I'm not going to worry about it. But we know that the magnitude of T is 1. So this is 1, this is 1 squared. So what I get is I get the projection of F onto T is find absolute value F dot T. If it's heading in that direction, negative F dot T if it's heading in the other direction. And I like to keep change in S always positive. So what do we say work is here? What will work be? Well, we said work was force times distance. So the force we're dealing with here is simply going to be F dot T, either towards the flow or against the flow. F dot T times the change in the arc length. So our total work then would be the sum of all of those. And you can see how that's leading us to our formula. So we know the work to get from here to here is going to be F dot T times the change in S. So the total work again is the sum of that. If the work is positive, you're going with the flow. If it's negative, you're going against the flow, which is why I can ignore the absolute value. And then as we shrink delta S to 0, we turn that into an integral. And we get total work is the integral over that entire curve of F dot T ds. So that's how we get that geometrically. Now let's turn it into a form we can actually use. So what do we know? What is the unit tangent vector? The unit tangent vector is in the same direction as the velocity, but it has length 1. So the unit tangent vector is r prime of t divided by the magnitude of r prime of t. And what about ds? We know ds is ds dt dt. So ds dt is the speed dt. So putting these things together, where does that get me? Total work is what? Total work is the integral over c of f dot t, r prime over the speed, times ds, which is speed dt. Well, you can see that we lose the speeds and we get total work is the integral over c of f dot r prime of t dt. But this isn't even how we remember it. There's one more step that we want to go to say total work is the integral over c of f dot dr dt dt. And here's the formula that we typically work with to say total work is integral over c of f dot dr. So a lot of geometry going on there to convince ourselves that's how we determine the total work done by a vector field over a curve C. That's the line integral we want to evaluate. So let's take a look at a quick example. So here's our question. We want to evaluate the total work done by the vector field f, x comma y, on a particle that moves along the curve C, defined by r of t equals 3t plus 1t. So indeed, that is a line this time. So the work is the integral over c of f dot dr. So how are we going to do this? That's the integral over c. F is what? Is x comma y for now. Dot dr, we want to think of that as dr dt. dt. So we can start making our substitutions. Moving away from c towards t, t ranges from 0 to 1. X comma y becomes what? The x value is 3t plus 1, comma, the y value is t. What is dr dt? Dot dr dt? Well, that, of course, is the derivative. Dr dt is r prime of t. Which is what? The derivative, that would be 3 comma 1. dt. What do we get for our work? Integral as t goes from 0 to 1. 3t plus 1 times 3, taking our dot product, plus t times 1 dt. Where does that get us? Equals the integral as t goes from 0 to 1. 3 times 3t, 9t plus 3 times 1 is 3, plus t dt. Integral as t goes from 0 to 1, 9t plus 1t, 10t plus 3. My antiderivative here is 5t squared plus 3t as t ranges from 0 to 1. 5 times 1 squared plus 3 times 1 minus 0 plus 0. And my answer is 5 plus 3 is 8.